All right, ladies and gentlemen, we're going to be talking about the thermo stations that you did yesterday. Please turn to page 210 in your lab manual. In our experiments yesterday, or the day before, first one we did, we were looking at heat. And we were looking at heat transfer between hot and cold water. And the variables we were looking at were we were changing the amount of water and the temperature of the water. And the thing we're keeping the same, obviously, was the same substance, hot water, cold water. Now we know if we add hot and cold water together, exactly the same amount of each, then you get it right in the middle, and that's what we normally think of as the average. When you have different amounts, the amount of energy being transferred from the hot to the cold, this here can be measured here in terms of what is called heat. Now heat is not the same thing as temperature. It's the energy transferred from one object to another, but it does involve the motion of the particles. And remember, temperature is the average kinetic energy of all the particles. This here is the equation where Q stands for heat, M is the mass of the sample, C we'll talk about is what's called the specific heat, which depends on the specific substance, and delta T is the final temperature minus the initial temperature, and that's always the change in temperature, whether it's hot or cold point of view. For the cold, it also was gaining energy, and it gains energy based on the amount of mass, specific heat, and change in temperature. Now this relationship means that the energy is always transferred from one thing to another. So if you add these two together, one will be negative, one will be positive, and the sum will be 0. This is known as the law of conservation of energy, and this here applies for all of the thermo reactions we did and the thermo changes we did. In this case, water's case, the specific heat of water, that's often abbreviated CP here, is in units of calories or joules, but we're going to use calories first. The calorie is of the amount of energy that it takes 1 gram of a substance to change 1 degree Celsius. Now water's value is 1 because water is the standard. So everything else is compared to water using calories. The amount of substance and the temperature of the substance and how much it changes determine how much energy is transferred. If you have one hot, one cold, it could go either direction, but it goes from hot to cold always, just depending on which one you have at which temperature. The specific heat capacity is defined as the heat required to raise the temperature of 1 gram of substance 1 degree Celsius. In calories, it's the standard 1. In units of joules, which is another unit, it is 4.184 joules. So if you had 1 gram of water and you added 4.184 joules to it, its temperature would go up exactly 1 degree Celsius. If you had 10 grams of water and you added, again, not 4.184, but you would have to add 41.84 joules for it to go up 1 degree Celsius. So you can see the amount, which is the mass, and the temperature, which is the average kinetic energy, and then the substance, that's what the CP stands for. Water and metals and other objects have different specific heat capacities, and those heat capacities are specific to the state of matter. If it's a solid and it's still a solid, you can use the specific heat. If it changes phase, then you cannot use the specific heat because a solid, a liquid, a gas all have different specific heat capacity values. Now this information here is provided on your reference sheet. This one here is not. This is the one that you have to remember for the reactions. In one of our other experiments, lesson 5, we added the metal to the water, and you saw that the metal's specific heat capacity may be different than the water. However, the same equation still applies. If you know one of the variables, you can solve for any of the other. In the chemical reaction we did, we put a chemical in water, and we saw that the energy that went out of the chemical either raised the temperature of the water or lowered the temperature of the water. If it raised the temperature of the water, then it was going out of the reaction, and we call that an exothermic reaction. If it lowered the temperature of the water, that means that the heat was going into the chemical that was dissolving in the water, causing it to break apart, and that's called an endothermic reaction. However, the Q for the water's point of view And the Q for the reactions point of view will still add up to 0, assuming no energy was transferred. And this here is what we did at station number 5. To do these calculations, you have to be very careful keeping track of your variables, and also the fact that the change in temperature equals the final temperature minus the initial temperature. If you get a Q with a negative sign, that means it's exothermic from the point of view you're looking at. And if it's a positive sign, the Q is endothermic from the point of view that you're looking at. Oftentimes in these different reactions, they often want the Q from the reactions point of view, or the Q from the metals point of view, and then sometimes they'll want it from hot or cold water. If you have a phase change, like a piece of ice, and you heat it up, the ice here will not change temperature as it's melting. So its temperature will go up until it reaches its melting point. This here for ice happens to be 0, and then once it all melts, then it can go up until it reaches its boiling point. For water is 100 degrees Celsius, and then it can continue going up as a gas. And this is the this is the gas that you can actually use to heat things up way above 100 degrees Celsius. The energy for a phase change is the energy needed for it to change from either solid to liquid or liquid to gas, or vice versa. If it's a positive sign, that means it's going up the graph. Negative sign means it's going down the graph for the Q value. And these here are on your reference sheet to allow us to calculate. Now if you're heating up water and you put ice in it, you have a phase change and a temperature change, and so you can have a few more of those Qs. So in calculating these, you're going to be doing practice problems over the next few days. Do your best on your lab. Remember, it's either this or it's a conversion. Good luck today, and we'll see you later. Bye.